You're listening to Pankaj Rai, and in this video we will be discussing the numericals of the chapter Electromagnetic Induction. So let us begin. Let's say that there is a strong north magnetic pole over here and there is a very strong south magnetic pole over here. And as you might be knowing, there are magnetic lines of force which begins from the north pole and goes to the south pole. So I am drawing few of the magnetic lines of forces. Now these lines of forces I am trying to draw them as equidistant from each other, which means that the magnetic field is uniformly distributed. Now we have to discuss about magnetic flux. That's why we are beginning with the magnetic lines of forces. So these are the magnetic lines of forces beginning from now north pole and terminating on the south pole. Now let us move ahead. Let's say that there is a rectangular coil which I'm placing between the north and the south pole. So let's say that this is the coil, which a rectangular coil which I am placing between the north and the south pole. Now as you can see that there are 8 magnetic lines of forces which are passing through the rectangular coil. This is the first one, second, third, fourth, fifth, sixth, seventh and eighth. Okay, also remember that the coil is placed perpendicular to the direction of the magnetic lines of forces. Now the first thing which we have to do is magnetic flux. Now what is magnetic flux? Magnetic flux is the number of magnetic lines passing through a given area. Now as you can see that let's say this is a given area, so there are 8 magnetic lines of forces which are passing through the area. So we will say that magnetic flux, it is represented by d phi. So d phi is equal to 8 in this case. Okay, now it is a numeric value, but the unit of it is Weber, WB. So we will say that magnetic flux passing through this area of the coil is 8 Weber. Okay, now let us move ahead. Let us go ahead with the next term. Okay, let's say the area of the coil, let's say A, it is also represented as ds, a very small area. Okay, so this is the area, and area would be, let's say whatever the area is, let's say it is 4 meters square. Okay, let's say the area is 4 meters square. Let's say that the breadth of the coil is 1 meter, and let me write it with a different color. Now let's say the breadth of the coil is 1 meter, and let's say the length or the height of the coil is 4 meter. Okay, it won't be meter square. So we are having here the area of the coil is 4 meter square, which is a rectangular coil. 4 times 1, so it is 4 meter square. So that is the area. Now the next important term is magnetic induction. Now magnetic induction is defined as magnetic flux per unit area. So it is magnetic flux per unit area. So it would be defined as d phi by ds. It can also be written as d phi by A, doesn't matter. And magnetic induction is represented by letter B. So in this case we can say that magnetic induction is magnetic flux upon area. The magnetic flux is 8 Weber and area of the coil is 4 meters square. So we can say that magnetic flux is 2 Weber per meter square. So that is the meaning of magnetic induction, which is the magnetic flux per unit area. And what is magnetic flux? Magnetic flux is the number of lines passing through a given area. So we are having our first formula of EMI over here, that magnetic induction B is d phi by A. Okay, it is we can also say that the d phi, which is the magnetic flux, is BA, which is the magnetic induction times area. Okay, now we have to remember this, and let us move ahead. Now let us move ahead with the Lenz law. Now, Lenz stated that whenever there will be change in the magnetic flux, now this is the magnetic flux which is given by the magnetic induction into the area. So whenever there is a change in magnetic flux, a EMF will be induced in the coil. That means a current will start flowing in the coil. Okay, so how does it happen? Let's say I change the magnetic induction. Okay, I change the magnetic induction of the field, so the magnetic induction will be changed, so the magnetic flux will change, and as and when there will be a change in magnetic flux, the EMF will be induced in the coil, current will start flowing. Or else if I change the area of the coil, let's say I decrease the length or do something which changes the area of the coil, so by that case as well the magnetic flux will change, and change in magnetic flux will bring about the EMF in the coil. So that is called as induced EMF. And the formula for induced EMF is given by mod of d phi by dt. That is, induced EMF is given as rate of change of magnetic flux. So if the magnetic flux is changing fast and magnetic flux is changing slow, that will also matter for the induced EMF. So EMF by Lenz law, which is induced in the coil which is placed in a magnetic field of induction B, and the area of the coil is A. So the EMF which will be induced will be given by change in magnetic flux with respect to time. Okay, now this formula can also be written as d phi E is equal to mod of d phi, the change in magnetic flux. Okay, so change in magnetic flux, let's say the final flux minus initial flux with respect to time. Okay, so this is another formula for induced EMF. We can also say that E is equal to mod of, now final flux will be something like we know here that flux is given by B into A, so final flux will be given by final magnetic induction multiplied by final area minus initial magnetic induction multiplied by initial area upon change in time dt, which will be t2 minus t1 or delta t, we can say. So this is the formula for induced EMF in a coil due to change in magnetic flux. So if we change the area of the coil or we change the magnetic induction, there will be a induced EMF in the coil given by this formula. Okay, now let us move ahead and look at the types of numericals which are asked on this topic. Now, this is the first problem for practice. Okay, it says that there is a wire which is 88 centimeter long. Okay, so I can say that the length of the wire is 88 centimeter. Fine. What's next? Now it is bent into a circular loop. Okay, and it is kept in a plane of a coil perpendicular to the magnetic field. I told you that coil is always kept perpendicular to the magnetic field, and the induction of the field is 2.5 Weber per meter square. Okay, so initially I can say that induction of the field is 2.5 Weber per meter square. Moving ahead, within 0.5 second, that means this is the change in time, the coil is changed to a square. Okay, so initially it was a circular loop and now it has been changed to a square, and magnetic induction is increased by 0.5. So there has been increase of 0.5 more. It was previously 2.5, so now there is an increase of 0.5 more. So I can say that final induction will be 2.5 extra 0.5, so that will be 3 Weber per meter square. Okay, and the change in time, that is delta t, or I can say dt, it is 0.5 seconds. Okay, now the major thing here is that the induction is changing. As you can see that initial induction is 2.5 and final induction is 3, so obviously there is a change in induction. Okay, and there is a time duration dt is given. Also we can see that initially the 88 centimeter long wire was in the form of a circle and now it is in the form of a square, so obviously its area might change. We have to see that. Okay, so obviously when the magnetic inductions are changing and the areas are changing and in the given duration, so obviously there will be a emf induced in the coil and we have to find out the induced emf. It is so simple. Okay, so we have to find out about the areas of the circle and the square. Okay, now let us concentrate. Now we have that length of wire is 88 centimeter, and now that wire is completely converted into a circle. Okay, now this is a circle. Okay, initially it was a straight wire of length L, now it is converted to a circle and I have to obviously find the area of the circle. To find the area of the circle I require the radius. Okay, so what is the relation between the length of the wire when it is converted to the radius? Now you can see the length of the wire would be completely converted into the circle, so length will become circumference. So I can say that we have here that L is equal to 2 pi r. Okay, now we have been given L here and we know pi, so we can find out r. So r will be we will have L by 2 pi. Okay, now the value of L is given to us in centimeter, it is 88 centimeter, and pi we know, and if you substitute this, we have L as 88 and 2. Let's take pi as 22 by 7. So 22 and 88 will get cancelled in 4, and 4 and 2 will get 2. So 7 2s are, so it will be 14. So I'm getting R as 14 centimeter. Okay, now I've got R, but what do I need? I need the area of the circle. We can also say that R is 0.14 meter, which is the standard unit. Okay, so to find the area of the area of the circle will be A is equal to pi r square. So A is equal to pi into r square. So pi is 22 by 7 into 0.14 into 0.14. If you do that, you get the area of the circular loop as 0.0616 meter square. So that is the area of the coil, okay, which initially was there. Now let us move ahead. Okay, and what we have to do is that this now the coil, the circular coil, has been converted into a square. Okay, so we can say that it has been straightened up, whose length is L, and now it has been converted to a square. Okay, let's say the side is S. Okay, now this length when converted to the square, so we can say that we can have that S plus S plus S plus S will be L. So we have that L is actually 4S, so that will be the side of the square. Now we know L, it is given as 88. We can find S, so S will be given by L by 4. L is 88 centimeter by 4, so S will be 22 centimeter. Okay, but what we need is the area of the square. Now S is 22 centimeter, so it will be like 0.22 meter, and area of the square is given as side square. So side square, so it will be 0.22 square. If you do that, you will get the area of that square as 0. It will be 0.484 meter square. Okay, so I can say that this is the initial area of the coil, which was in the form of circular loop, and this is the final area of the coil, which is in the form of a square. Okay, so what do we have here now? We have that initially magnetic induction was 2.5 Weber per meter square, and then it has been increased by 0.5. So we have the initial magnetic induction, and we also have the final magnetic induction. So initial and final magnetic induction we are aware of. Okay, now initially the length of the wire was molded into the form of a circular coil, and we just found out the area of that circular coil. So this is the initial area of the coil which we know, and then the circular coil is converted into a square. So this is the final area which we also know, and we are also aware of the time duration in which these things happen. So the question was, find the EMF induced in the wire. Now this is the formula, as I've already told you. EMF is given by final induction into the final area. So we have final induction over here, we have final area over here. You have to multiply them, substitute it here, subtract it by the initial area. I'm mistaken here, this is initial area. Okay, let me correct it. So this over here is the initial area. Okay, yeah, fine, it is now. So bi, which is the initial area which we know, okay, and you have to substitute the initial Bi is the initial magnetic induction, and Ai the initial area. You can substitute it here. Delta T is 0.5. You can substitute it here. If you substitute everything and do the calculation, you get EMF as, it will come as negative, but if it is coming as negative, it is under the mod sign. So EMF which you will get would be something like 0.0176 volts. So this much amount of EMF will be induced in the wire due to these changes. So this is one type of numerical on the Lenz law. So you can practice the others by yourself. Thank you very much.